I'm Marina Jurica with NASA's Jet Propulsion Laboratory in Southern California. After landing on Mars last week, NASA's Perseverance rover took its first look around. We are getting an initial look at just how powerful the cameras on board the rover are. From the never-before-seen entry, descent, and landing video to the Mastcam-Z camera system, capturing a panorama of the landscape in unprecedented detail. We have been able to see the surface of Mars as never before. The Perseverance rover has 19 cameras on board, ready to explore. Today, I am joined by a team of experts who will be using the Mastcam-Z camera system throughout the mission, and they will show us the highest resolution shots of the red planet yet in a moment. If you are joining along in the conversation and would like to ask one of the scientists or engineers a question, you can pop it into the social feed you are using with the hashtag Countdown to Mars. Joining me today is Jim Bell, the principal investigator for the Mastcam-Z instrument, Elsa Jensen of Malin Space Science Systems, who leads operations for sending commands to the Mastcam-Z instrument, Kjartan Kinch of the Niels Bohr Institute of the University of Copenhagen, who led the design and construction of Mastcam-Z's calibration targets, which are used to tune the instrument's settings. Thank you so much for joining me here today, guys.
Great to be here, Marina. Thanks for having us.
Yes, thanks for having us.
Thanks for having us.
Now, Jim, we spoke before landing on your anticipation for the camera shots you would be getting. Is it living up to what you dreamed it would be?
Oh my gosh. Oh, I mean, remember when we talked about it and we were trying to make predictions and I made a crazy prediction. This is going to be a feast for the eyes, right? All these incredible cameras. You mentioned the 19 on the rover. If you count the ones on the descent stage, if you count the ones on the helicopter, we're talking about 25 cameras on this rover. Just unbelievable, image rich. And I think we were all blown away by the videos, right? By those incredible, the parachute and the thing and the stuff. And it's like, what? It's just really hard to believe that all that worked, even though many of us kind of knew intellectually what to expect. Emotionally, it was like we were blown out of the water. It was incredible. And a lot of us are having, on the Mastcam-Z team, are having the same experience with the pictures we're taking with these zoom cameras.
Absolutely breathtaking. I think everybody around the globe has just been so inspired by it all. Now, you mentioned that the first images you ever saw of Mars were from the Viking landers. Now, how does that compare with what you're seeing now?
Yeah, so, the first successful landing on Mars back in 1976, and the two Viking landers, 1 and 2, set down on the surface, and very different camera systems than we use today. But for the time, they were designed and built in the early 1970s. They were just incredibly cutting edge, incredibly state of the art, but also very simple compared to today's cameras. The Viking cameras had basically single detectors, and they were scanned up and down and then moving along the side, kind of like a fax machine almost. And so I remember being a kid watching on the nightly news the first pictures coming down from Mars, and they were coming down in these little strips like, and it was like watching paint drip down the wall, and little bit at a time, and it took hours, and you see, oh, there's the footpad, and it was incredibly exciting. Of course, the first time we got down onto Mars. Nowadays, we're used to digital cameras in our cell phones or DSLRs. We're used to big arrays of pixels, megapixel arrays. And so, Mastcam-Z is a 2-megapixel camera, which is pretty good for space. There are higher megapixel cameras on this rover, but for us, it does the job. And its resolution varies because, of course, we go wide angle all the way to telephoto in stereo with those two eyes here you're seeing in this next graphic, the two eyes of Mastcam-Z up on the mast. And that mast can let us move around 360 degrees up and down. And that's how we build panoramas. And you'll hear more about that from Elsa. At the widest setting, we get about 2.5 times better resolution than those Viking cameras. And at the telephoto setting, we get about 10 times better resolution than those Viking cameras. So those are great start to the legacy of imaging on Mars that we're picking up with this mission.
And what an amazing opportunity, Jim, for you to be able to watch that growth. This is your 5th Mars landing, and to be able to watch just exponentially how these cameras have gotten better and better. So what kind of advice do you have for the future scientists and engineers watching today on what they will bring perhaps to the table coming up?
Yeah, we've got a lot of young people and early career people here at ASU working with us, faculty, staff, students. I'm in the Mission Operations Center for Mastcam-Z here at ASU on the Tempe campus, and so we do a lot of the processing here. And I think what's happening is, these students we work with and others, they're seeing the future of deep space imaging, these video cameras with these higher and higher megapixel capabilities, with more infrastructure out in the solar system to get the data back. We can talk about bandwidth and how, we can take megapixels and movies and all kinds of stuff, but we don't have high-speed internet to Mars, right? We have basically the equivalent of old-style dial-up. So that's advancing that frontier. We're seeing incredible improvements in our mission compared to previous ones in how we can get all those pixels into the tiny straw of bandwidth getting back to the Earth. So I think that's just going to continue to improve, and we'll continue to send amazing missions out there, and the instruments are going to get more and more sophisticated, basically following the consumer electronics and all the great, amazing things that are happening in digital imaging in our everyday lives.
So much to look forward to as we look into the future. And speaking of that, you said it's been a feast for the eyes. I don't think we could ever get enough of that. So moving over to Elsa. Elsa, how do we actually take these pictures on Mars?
It's amazing, actually. We started 2 years ago. And if I could have the mosaic image number 3. Number 3, please. It actually, from start to finish, to take a picture like this in the box is about 2 years. It's taken a core team of 6 people, starting 2 years ago, to plan, test, and execute over 5,000 command parameters that go into this image. And we took it only 3 years after landing, which in Mars mission time, is just a blink of an eye. You land and we already have to execute it. So we had to start a long time ago. It's funny because when you take a panorama like this on Mars, you're thinking, oh, it's very technical, and it is, but it's in some ways the same as when you have your smartphone, because what you need to do is you have to look in the right direction, and you have to get the focus right. And that's really what we focus on when we're taking these images. We're millions of miles away, though. Our selfie stick, if you will, is 150 million miles long. So when we take the pictures, we can't just go out and do it. And when we press the shutter button, hey, take a picture, it takes a day for the signal to get to Mars. And it takes another day before we get the images back. So we have that challenge of time and space, if you will. So how do we do that then? We use our experience. We've been doing this for a long time. We've actually been imaging for 8 years with Curiosity, with the Mastcam, and that has led to a ton of experience. We use our intuition, and then we have computer tools. And as we put all these things together, we make a draft, we test it, we get results. Some of them work, some of them don't, and then we test again. So I wanted to introduce one of the most important tools that we've used in creating mosaics, which is the command visualization tool called Viewpoint. And it was developed by one of our team members, John Proton. And it provides us with a way to visualize as if we were on Mars, looking at the Mars images behind it and the computer model of the rover. And then we can lay down footprints. And that's a great way to pretend that we're right there with Mastcam. As you saw the pictures before, we're right there with Mastcam taking the images, and be able to visualize that. So if I could have the next picture, please. Thank you. You see here the frames. See all the red squares, the red rectangles? That's actually the footprints that we've laid down for this mosaic. And there's 142 total. Like I mentioned before, there's over 5,000 commands for altogether to take these 142 images that we stitched together. Now, in this case, we didn't land on Mars before we took this, right? We had to plan it in the blind. So we had to start with our information that we had available, which was from Curiosity. So 2 years ago, two of our ops engineers at the time, Jason Van Beek and Tex Kobaczki, put together kind of a draft. And then that sequence we took into testing with the thermal vacuum chamber, which is house size. So imagine a small house that is in Mars conditions with the temperatures fluctuating about 100 degrees between day and night, and also some of the air pumped out for vacuum. And we tested in there. And then we also got special permission to execute this sequence at Kennedy Space Center. And that was important because of the focus. We could get the landscape pretty well from Curiosity, but we also needed information on how to focus on the various details of the Perseverance rover deck, because that's different than Curiosity. So we got that in the bag, and thank goodness, because that's what allowed us to put the sequence together, all of it in one sequence. We sent it up 2 weeks before we actually landed on Mars. We do that to ensure that as a mitigation in case there are communication errors right after we land, it was all fine. But in case, we would have it on board already and ready to execute when we landed. So that's part of the thorough testing that we do when we're preparing to go to Mars. So as we got finally, with all of that, we had our cognizant engineer, Mike Kaplinger, here at MSQ. We had ops engineers, Tex and Angela and Chris and myself. We checked and rechecked, and then we were ready to fly. So if I could have the next image, please. Here's how we laid out the panorama. You see how we start at the horizon, where imagine being on the mast, you're looking one way and then looking next down we go as we take the panorama and building up tile by tile from the horizon and all the way down to the rover deck. 142 different frames. You can see we have focus on the hardware, on the landscape, and it's all put together into one sequence. So it's great to be here today. Our team is loving being on Mars. We're taking already hundreds and hundreds of images with this camera, and we're going to take thousands, tens, if not hundreds of thousands in the future. We're so happy to be here from Malin Space Science Systems and love working with Jim and ASU. Thank you for having us come along to Mars again. And we just cannot wait to get going with this camera. Thank you.
Awesome.
Thank you so much, Elsa. Such great information. And that was such an incredible animation there as well. And it obviously takes a village to get all of these images processed and put out to the public. And Kjartan, what's a calibration target and why do you actually need one?
So all scientific instruments basically need some sort of calibration. You need to make sure by imaging or measuring some standard, something that you know really well, you need to make sure exactly how the readings of your instrument translate to things in the real world. And we went through a lot of pre-flight calibration, a lot of activities to image lamps and dot patterns and other things with the cameras to make sure that we understood these instruments really well. And a lot of the instruments also have calibration targets on board the rover that they can visit, and we have a calibration target that we can image to check that things are still operating as they should. But our calibration target actually kind of has a purpose that goes a little bit beyond that. And the reason is the Mastcam-Z is a color camera, of course. It acquires color images in red, green, and blue, but it also has a whole set of special optical filters, or what we call narrowband filters, that are basically filters that image at sort of tightly around a single frequency, a wavelength of light. And we have 11 different of them, from a little bit into the ultraviolet, a little bit out into the infrared. And with all of these different 11 narrow and 3 red, green, and blue, with all these 14 color bands, we can make some color images that allow us to go a little bit beyond human vision and tease out differences in the terrain, tell one rock from another, or tell that 2 rocks are similar, or tell layering in a cliff face, or what have you, and also in things that might not be visible to the human eye, to standard red, green, and blue. But when you look at a rock on Mars or a rock on Earth or anything, you're seeing a color that's a combination of the color of the light and the color of the thing, the rock. So you shine red light on something, it looks red, and you shine blue light on it, it looks blue. And on Mars, the illumination will change like it does on Earth. The sun may be high in the sky, maybe low in the sky. The atmosphere may be dusty, it may be not so dusty. So it will change over time, and it can change on fairly short time scales, and it's kind of hard to model. So for that, we use the calibration target. And can I get slide number 7 with the calibration target? So that's just a little aluminum plate with some patches, ceramic patches in 4 colors and 4 grayscales and 4 rings in the same grayscales. And these are colors and grayscales that we characterized super well before we flew to Mars. So we know exactly how they reflect light. And so imaging this with the camera allows the camera actually to measure the illumination, measure the light that comes in. And then we take a picture of Mars, and then we can use that information to basically divide out that illumination. And we can then convert the image of Mars to what we call a reflectance calibrated image. And that's an image that shows the inherent color of the rocks and the soil, how they reflect light rather than the illumination. And that way you can compare them to images you took 10 days back when the atmosphere was dustier, or image you have of a rock in your laboratory, or whatever. And that helps the science team use the camera to pick out interesting targets and so on. If you give me the next slide, is a close-up of this calibration target. And we're going to be imaging it a lot. And so we added some decorations and a little model to it. And it's just been an amazing journey. Seeing it for the first time on the surface of Mars was amazing. I'm sitting here, and it's 10 p.m. in central Copenhagen in the Niels Bohr Institute. I'm actually sitting in Niels Bohr's old office. He was one of the fathers of modern physics, and they let me sit in his office. They've left it preserved since he passed away in 1962. And everybody here that has worked on this project have just been so excited to be able to contribute to this amazing mission and be a part of this amazing team.
Kjartan, that's amazing information here. And I actually have a social media question that's coming in that really pertains to what you were just talking about. Joshua Becomes on Twitter says, this is really incredible to see. I'm sure we all think that. Now, are these photos artificially colored?
No, I mean, I know, Jim, if you want to.
Well,
sure.
Kjartan pointed out that we've got all these different color filters, and when we take pictures like this panorama in red, green, blue, then it can simulate what we see with our own eyes. But if we use the filters that are a little in the ultraviolet or a little in the infrared beyond, I call it superhuman, Mastcam-Z has superhuman vision, then we can't look at them in red, green, blue, so we have to false color them. Kind of like a lot of the pictures you see from the Hubble Space Telescope. They're taken outside of human normal vision, and they're false colored. And so you'll start seeing, once we start using those filters, and I know Kjartan's going to do a great job calibrating them, you'll start seeing these kind of Andy Warhol, garish views of Mars that don't look like what we see it with our eyes, but that look just like what Mastcam-Z can see with its superhuman eyes. And like Kjartan said, that gives us some sensitivity to different kinds of rocks and minerals and just color variations. And I think of us as using the cameras kind of to do triage. You know, we can sweep these fields of view across the whole scene with the navigation cameras, the hazard cameras, and Mastcam-Z. And we're using color differences as a proxy for, well, maybe there's a really interesting chemistry there. Maybe there's interesting minerals there. Maybe there's an interesting texture. And we'll drive over and use all the ARM instruments that we'll be seeing and hearing a lot about in the weeks to come, use those to get the much more detailed information.
And I know, Jim, you made an incredible storyboard with your teammates, and it really shows truly how this camera can zoom.
You want to take a little tour through this? Should we do that?
Yeah, let's do it. Let's do it.
All right. Well, so we're going to start. This is the full version of the panorama, 360 degrees. It connects on the left and the right. You could wrap it around, and it goes right down to looking at our feet, out to the horizon, and a little bit of the sky as well. So go ahead and zoom to the first region here. We're going to zoom in on this panorama all the way behind the rover. This is looking to the north, a little bit northwest, and you can see a couple of different ridges. There's a near ridge closer to us, and then there's those far mountains. The near ridge closest to us is the front edge of the delta, the Jezero Crater delta that brought us to this site, that brought this rover to this place, and that we're going to eventually drive over to. Beyond that, those distant mountains are the rim of Jezero Crater. You know, Jezero is a big hole in the ground. It has these mountainous circular rim of mountains that surround us, and we're seeing them all on the edges of this this panorama. So those are pretty far away. Those are 3, 4, 5 kilometers away in the distance. But the delta itself is only about 2 kilometers, a little under a mile and a half or so away. So it's relatively close. The engineers got us in a beautiful spot. And let's zoom back out and just look at a couple of the features. A number of the science folks on our team have been looking at these different areas and zooming in and trying to do some instant science and analysis. And let's go to the first zoomed in region here. You're transported. You can see the resolution of the panorama, right? We keep going in there, and it's like, wow, look at this detail. This is just a blocky hill that we think is a separated remnant, maybe, of the original delta. Maybe the delta was much larger and it's been eroded away, but leaving these little blocky remnants behind. We see, some evidence that it might be more resistive on its top. This is obviously our first look at it. We're going to be getting much higher resolution data. This is our widest angle zoom, so our lowest resolution almost on the camera. So we're starting to telephoto in to these now over the coming days and weeks, and we'll get much more detail. And then, of course, to get even more detail, we'll drive over there or somewhere near there. We'll get closer to these features. Let's go to the next one. So zoom back out and get a sense of, again, the wide scale, right? Now let's zoom into the next one. I think this is going to be another part of the delta. This is farther towards the north and west part of the delta. See some, again, this blocky kind of top to it. There's the faint hints of some layering in here. Maybe, we would expect that from what we've seen from orbit and from what we know about deltas, but it's really kind of a tease because we, of course, want better resolution, and lots of folks thinking about what could be going on here. Lots of sort of geologic comparisons to what's going on in deltas and other places on the Earth. Let's zoom out and look at some other features that are really close by, some individual rocks and other rocky regions. We'll go to the next one. I think this is going to go to, this is an area pretty close to the rover that's been scoured by the retro rockets coming down and delivering the rover on the sky crane. So some of the dust and soil has been scoured away, exposing these rocks with some layers. That white rock in there is about a half a meter across, or about 1.5 feet across for scale. Interesting features and textures on it. We don't know whether these are volcanic, sedimentary, some combination of them. We don't have chemical and mineral data yet, but again, the cameras are helping us triage and identify the places where we want to get those detailed chemical and mineral measurements. Let's zoom out and go to the next one. We've got 2 more here to zoom in on. I love how you get a real sense of the resolution on this panorama. Here we go. We're going to another interesting, weird little rock. This one is also about 1/2 meter across, about 1.5 feet across, and it is informally been called the harbor seal, and it is a highly eroded, probably wind-carved rock. And we've seen rocks like this at other Mars landing sites. These rocks have been exposed to the winds of Mars for billions of years, and you'd think that the sand grains, gently moving across the surface wouldn't do much erosion. But if you let them do that work for 2-3 billion years, you can create these just fantastic forms in the rocks. These are called ventifacts on the Earth, and we do see these kind of wind-carved features. We think they're wind-carved features, at least. We need to get over and take a closer look or get the high resolution on it to know better. And even one more, we'll zoom out and zoom back into one more. And these, I think, are this area, which is going to be to the right here, is even more enigmatic and some of the most interesting stuff we're looking at. These are light-toned, pitted rocks that, again, part of the dust and soil that was covering them has been blown away by the retro rockets. Hopefully, you've all seen that movie about the crazy structures and the winds moving when the retro rockets came down, almost like it was alive. It's just phenomenal stuff. So this has all been kind of cleared off a little bit. And are these volcanic rocks? Are these carbonate rocks? Are these something else? Do they have coatings on them? We don't know. We don't have any chemical data or mineral data on them yet. But boy, they're certainly interesting. And part of the story about what's going on here is going to be told when we get more detailed information on these rocks and some of the other materials in this area. So let's zoom back out again. And that just gives you a flavor for what you can do in exploring this panorama on your own. The NASA photojournal site has released the full resolution TIFF file. If you want to download that, it'll take a little while, 650 megabytes or so. But you want to wallpaper your bathroom with Mars, that's the file to use, highest possible resolution. And there are many of us on the team are just giddy and spending hours just pouring through this and place to place. It's a lot of fun.
We've been spending
years. We've been spending years looking at this site in satellite images from orbit that are like, 25 centimeter per pixel, which is amazing from orbit, but getting down on the ground and being able to, pretty much maybe soon know what this all is and puzzle out the story is just super exciting.
Very exciting.
And I'm sure that's a general reaction from your entire team. I mean, we're taking a Zoom tour of the red planet, and that just incredible detail. I don't think a lot of us ever thought in our lifetime to expect.
Yeah, it's pretty spectacular, and more is coming. Remember, this is our lowest resolution panorama. We will get 3 times this resolution, and we're starting to get 3 times this resolution on selected targets in the field. And we'll pick that up in earnest once we come back from the software transition that's going on now. We're going from the cruise software to the surface flight software that takes several days. And so once that process is done, we'll get back to characterizing our cameras. The other instruments will they need to do their calibration, their characterizations. So the whole rover is just sort of slowly coming alive, slowly turning on as the engineers check out system after system. We're very lucky to have been turned on and starting our checkouts very early and getting all this great stuff out very quickly to the public, including the raw images that went into this panorama, which have been released on the JPL NASA Raw Images public website.
And as you might imagine, we've got so many people joining us today on social media. And if you want to have your questions answered, remember to use the hashtag #CountdownToMars. So let's get to a few of your questions out there. We've got a lot of them. A YouTube viewer asks, are the Mastcam-Z pictures used for stereo vision 3D mapping of the surface?
Yes. That is a major, major goal of what we want to do. And it's an advancement that we're able to make over the Mastcams on Curiosity, which Elsa and her team at Malin Space Science Systems operate still every day. 3,000 odd Mars days after landing back in 2012. So that those cameras, which fit on the same mast, we have a copy of that mast on Perseverance. Those cameras have one wide angle left eye and one telephoto right eye. And they take spectacular pictures. They're just amazing. You've seen the pictures from Curiosity. The problem, in quotes, problem, is it's hard to do stereo. You know, you have to do stereo at the wide angle scale, so it's low resolution stereo compared to the telephoto lens, and it's just cumbersome to do it, and you need a lot of telephoto images to fill in, and so it's just not as easy and common to do 3D stereo with the Mastcams on Curiosity. So the innovation that we brought with our partners at MS-Cubed was to design this zoom system so we could do stereo at the wide angle like we've got here, and then all the way to telephoto. So there's a right eye, this is the left eye, this panorama you're seeing here of Mastcam-Z. There's a right eye version of this, much of it is still on the rover. We're trying to get it down as quickly as we can. And once we get all the right eye data down, we'll take the left and the right, and we're going to get a beautiful stereo view of this terrain at that scale. And we'll be doing that left-right at all of our zoom positions for everything that we do. And we use that stereo information not just for science and the geology and the topography, but to help our engineering friends and colleagues who are driving the rover, who need that stereo vision to do hazard avoidance and traverse planning, to guide our friends on the helicopter team who are trying to find a safe landing site, takeoff and landing site for the helicopter. They need stereo data, so Mastcam-Z can help with that. To guide our friends putting the arm down and the drill down onto the surface, they need stereo data. They can get it from the nav cams at lower resolution. We can give them even better stereo data with the Mastcam-Zs. So doing that kind of stereo is 100% part of our goal, and we're going to put a lot of those great stereo products out for the public to enjoy as well.
Great, Jim. Another technical question from Facebook. Ira Colley asks, what is the transfer rate, bandwidth and speed of data to the rover from the Earth?
Oh my gosh. Do you happen to know that, Elsa? What's the uplink rate?
Well, I don't happen to know the number, but one thing that is an interesting number that I just heard the other day, which is, we start really low because we have to make sure everything is working. So you start on your really safe antennas that have lower transfer rates. So that's how we started, and we couldn't get very much up or down. That's also why we had to put our first 4 days of commands on the rover beforehand, because we were really starting out. We wouldn't be able to send it all up in the beginning on these really low rate antennas. But very quickly on this mission, after we landed, everything was A-okay, and they upped the transmission rates very quickly. And I just heard one of the mission managers yesterday tell us that at this point in the mission, comparing Perseverance to Curiosity, we have about 10 times the amount of data coming down every day that we did 8 years ago when we landed. And that's thanks to the systems working really well, and also that we have more orbiters, more assets at Mars that can relay out data for us and get all this data down. Otherwise, we would not have had this much data down already.
Yeah, that's true.
We
I think the numbers are in the hundreds of kilobits per second. I think that's...
We can go to the mega, yeah. We can, yeah.
And Christopher has a follow-up to that question on Facebook as well. How much longer does it take to receive Mastcam-Z data due to the larger data sets?
Yeah, that's a great question. That's a great question. And it's a little complicated because we're not in real-time contact with the rover. When Elsa said it takes a day to get the commands there and a day to get back, it's not because it's a day at the speed of light. It's because it's a day on our work calendar, right? It's because we communicate. We send the commands up to the rover approximately once per Earth day, once per Mars day in the morning when the rover wakes up. First thing it does is it listens, hey, Earth's going to call me with my to-do list today, and radio that up, the deep space network that NASA runs, gets its command list, and then we're out of contact with it. And it's just executing all those commands, take these pictures, test that instrument, turn on this heater, wiggle the wheels, drive 2 meters forward, whatever. It's just a long to-do list with timestamps. It's doing it on its own. And then near the end of its day, one of the orbiters, NASA or the European orbiter, comes overhead and the rover relays its results back through that orbiter and then back to the Earth. And sometimes it comes very quickly, sometimes there's a little bit of a delay. But the end result is we're really getting a big pile of data once a day, maybe twice a day. Sometimes in the middle of the Mars night, we get one of those orbiter passes as well. And so we're not joysticking, we're not in real-time contact. But at least in the first part of this mission, almost all those bits of ones and zeros coming back to us have been images. The videos that you saw, these spectacular panoramas, lots of engineering data and telemetry, but the imaging data is the vast majority of that stream of radio signal.
All right, let's turn to the freezing cold nights of Mars. Taryn on Facebook asks, will Perseverance send in a night landscape shot?
Well, the thing about yeah, absolutely. What I really encourage people to do is imagine that you're the camera on Mars, because our mass is up, and actually the mass is at about 6 feet. So as we look around, it's almost like you're standing there yourself looking around. And they are visible cameras. They're primarily in the same wavelength that you can see with your eyes. And so if you're there at night on Mars, how much could you see? Well, it's really dark, so we can't see a whole lot. And that's where we're at. We're not going to take images at night for that reason. And also because it's extremely cold. I mean, I was just looking at our temperatures the other day. We get down to minus 80 degrees Celsius on our cameras. And we do have heaters on board. We use them even in the morning or later in the afternoon when we need to. We use the heaters, but that much energy to heat us up that much in the middle of the night, that would just be prohibitive. So you got two things against you. You got no light and you got too cold of a temperature. So we generally don't do it, except for a few occasions when we might be looking up into the sky and doing that at nighttime. But we do have to set it up beforehand. Again, we don't want to heat everything up. It's the cameras, it's the mast, the massive mast that you saw. That has to be heated as well. So you want to set it up beforehand. So all you have to do is open the shutter to take the image and then be done with your job.
I'll just add that, you're absolutely, that's a great description, Elsa. And, the science goals of our mission are focused on geology, mineralogy, chemistry, also atmospheric science, typically daytime, but the weather station, the meta weather station, will be measuring nighttime temperatures and pressures and all that kind of stuff. So for imaging, it's difficult at night. These are cameras, not telescopes, right? It's not like taking your big light bucket telescope out in the yard and collecting faint signals. These are just cameras. So, if you just point and shoot with your iPhone or your Android phone, it's hard to get deep space astrophotography kind of data out of that. So we can see bright stars, we can see Phobos and Deimos, the moons of Mars, and we'll do some of that science. We'll do some of that nighttime science. It helps us understand the atmosphere and the moons themselves. And it's sort of great bonus science if we have the power to run the heaters, if we have the power to run the cameras, if there's scientific questions and scientific interest that we can direct at it, we'll do that. And we'll also, I predict, nothing is formally planned, but I predict we will do some relatively fun kind of things, like take some pictures of the Earth. This has been done on previous rover and lander missions. We will take one, these are the ultimate selfies, right? Everybody on the Earth in that one pale blue dot in the sky. And so we'll probably do some sort of fun stuff like that too.
And speaking of atmospheric science, Glenn on Facebook asked, does condensation form at night on Mars?
Kjartan's the physicist, so he should take that question.
Well, it happens. Probably not that much here because we're close to the equator, and there's not that much moisture. There's actually some pretty amazing images from Viking with frost on the ground. So it happens, but it will be frost condensating because the atmosphere is so thin that the water can be a gas or it can be ice, a frost, but it cannot be liquid. And so it will go to frost on the ground, and then it will go straight back up in the atmosphere. But you can get, like, especially if you're not on the equator or close to the equator like we are, you can get like a frosty morning that like you can get here on Earth.
And Rachel on Facebook asks, how do you deal with dust on the lenses?
Well, that's a great question. I get that question every single time. That's a wonderful question. We actually we don't do a lot about it. Actually, we mitigate. We prevent dust from collecting on the lens by pointing the cameras down when we're not using them. That end of the mast, we just point it down, and that prevents the dust that's always falling gently out of the atmosphere from collecting on our lenses. But we know that dust is going to collect on our lenses when we're imaging, and especially up at the sky and all that. And we can't point down all the time. And we don't have any little wiper blades or anything like that. No covers to protect them. So we know that the lenses are going to get a little bit dusty over time. And sort of two things. One, if anybody who wears glasses, I wear glasses, I wear contacts, but I also wear glasses. You take your glasses off and just look at them. Elsa, look at your glasses. They're probably kind of filthy dirty, right? They've got dust all over them and specks and hair. But you put them on and you can still see through them, right? And it's not that bad to get a little bit of dust. And so we can live with that. And if it does get a little thicker, we can correct for that with our calibration that Kjartan and others are working on. And secondly, what we've discovered in previous missions is that once in a while, the winds of Mars come and they blow the dust off the deck of the rover, off the calibration targets, off the lenses. And so Mars has been actually pretty helpful in past missions in keeping our lenses clean. But our prevention is really kind of passive and just point them down.
I'll add a little something to that, because exactly this reason of the dust is why we had to get going really quickly with our imaging. We wanted to take images as soon as we could of a clean rover deck. Well, as Kjartan can attest to, it wasn't entirely clean because, all the dust that was kicked up. But specifically for Kjartan and the other scientists on our team, Jim being another big proponent of this, we wanted to look at the deck as cleanly as we could so we can compare that to all the data that comes after. And that was one of the big reasons we were allowed to image as early as we did. And in fact, even the day before we imaged this one, we took a huge amount of calibration target data. And that was really so that the calibration could compare to that for the rest of the mission. And we'll continue to do that and monitor, take images on a regular basis to monitor the dust that's accumulating. And it's my understanding, Kjartan, that there's some special places on the Cal Target that deals with dust.
Maybe
yeah,
we could show
if you can
image
put
8
up
again.
slide 8, image 8. So it's obviously a problem for the calibration target too, and that is always facing upwards, and dust will drizzle on them. No, slide 8, the major slide 8. So they will gradually get dusty, and sometimes the dust will get blown off a little bit, and they will get dust. That's the one. And actually, right at landing, there's a bunch of dust that gets kicked up by the rockets, right? We wanted to image it right after landing as quickly as possible. That's the cleanest it's ever going to be. But it has these, you can see how the dust just rings around the patches. And that's because we build in these very strong hollow cylinder magnets that are sitting right underneath those surfaces. And they attract the dust to where the magnet is, but in the middle, the magnet is not. And that area is kept fairly clean of dust. And that will work also for the dust in the Martian atmosphere. It works because there's iron in the dust, both in this dust and in the dust that comes drizzling down from the atmosphere. So those magnets are going to keep those little areas pretty much clean of dust. And those colors are going to be like they were in the lab when we measured them. And we're going to be trusting them still. But another thing is that on other parts of the calibration target, it will gradually get dusty, and we will be able to monitor that. And that's actually kind of a little extra piece of meteorological data, because we can sort of tell when the dust is falling and when it gets blown off, and it's like a seasonal thing on Mars.
I'll mention that Kjartan wrote a great blog piece on our public website, and Marina will give you the address at the end, all about this target and all about the magnets and why the colors were chosen and the little messages and vignettes and all that, and the sort of artistic elements that we were able to put on this with help from the Planetary Society and Mark Hilverda, who's an artist who works with the Society, and a small group of us on the team. So I encourage folks to check out Kjartan's article that's on our website.
And speaking of that, for Kjartan, J.E. Bruce on Twitter wants to know where he can get his hands on one of those sundials. And can you tell us more about the sundial?
Maybe I should start a company and just crank him out and sell them.
That's right.
We have a few spares. When you send an instrument, you have to build a flight spare in case something goes wrong with the instrument before you launch. So we actually have 2 flight spares. They're not for sale. And we have a few extra sort of test units, but it's only a little handful, and they'll probably wind up in museums where you might be able to see them. Tim has a 3D printed version there, and we do have 3D print files that maybe we'll put out at some point.
Maybe we should put the 3D print files on our public website if you're willing to do that.
Yeah, we could do that. Yeah, sure, absolutely.
So this just gives you a sense of scale. This is full size.
Yep.
So there it is. And we did have, you mentioned museums. We had the flight spare for the Spirit and Opportunity Cal Target was on display in the Smithsonian for many months.
It was cool.
Special exhibits about those rovers. So lots of people put their eyes on that one.
Yeah, I remember I went there, Jim, and I wrote that I just came back from standing in the August presence of the Apollo 11 command module, and you wrote back, how about the August presence of the Spear PanCam Cal Target?
Yes.
And I said that was a flight spare. It wasn't a flight Cal Target.
Yeah.
Anyway.
Well, as a meteorologist, we're getting tons of weather questions. So I'm really excited about that. Everyone is very excited talking about the weather on Mars on social media this afternoon. Chopra on Facebook asks, any storms expected there, and how do you manage them, and how would they affect the Mastcam-Z?
Yeah, I mean, we don't manage the weather. We do not manage it. Absolutely. But you know, the great thing about the fact that we've had 60 years of exploring Mars with flybys, orbiters, landers, and rovers is that we really know a lot about the weather, and it is very repeatable from year to year. Not precisely. Some years are different. Some years have these big dust storms that cover the whole planet, and we don't really understand why those form in some years, not others. But in general, you know, everywhere on Mars has a dusty season and a less dusty season, and there's always small dust storms all the time, and sometimes it's cloudy and with water ice clouds, and sometimes it's not. But we understand a lot about those patterns from these previous missions. And so, you know, we landed at a time that's not particularly problematic for dust storms, but there will come a time when there will be more of an issue for dust. It's not so much of a concern for Perseverance and Curiosity, nuclear-powered rovers, as opposed to the solar-powered rovers, Spirit, Opportunity, and solar-powered missions like InSight. You know, ultimately it was Mars dust and dust storms that killed both Spirit and Opportunity because of the dust settling on those solar panels and the dust darkening the sky and cutting off their solar power. So we care about the way it changes temperatures. We care about the way it could mess up our lenses. So we do follow it and track it and pay attention to it. But honestly, we mostly care about it scientifically because it's a really interesting part of the weather. And we're trying to learn as much as we can about the weather on Mars so that once future astronauts and settlers go there within the next few decades, they'll have a really good understanding of what to expect and when at different times of year. Elsa.
And then there's also a little story about how we captured some sand in the cameras with Curiosity. Right. That gave us a nice lesson learned for this mission. So what happened was during dust storms on Mars, sand would deposit. We have these long lens covers that keep stray light from coming into our images. Well, they're also really good at trapping small amounts of sand. And we didn't even think about this until one day when we were looking up at the skies, we talked about, and we take images, you know, at different angles to look at the atmosphere. And we noticed there seems to be something off. There's definitely something off in these measurements. And we looked into it further and we compared, you know, over time, how did this exhibit itself? And Mark Lemon, who's one of our most prominent atmospheric scientists, looked at his data as well. And we realized there's something in front. There is absolutely something in front. So we took some experiments and we determined that, yes, indeed, when you go up and when you go down, it looks different. Just very proof, really, strong indicators, we say in the scientific world, that we had sand inside the lenses. Well, you can't just go up there and sort of shake it out, right? That's not how it works. So we still have a little of it inside the covers on Curiosity. And what we learned from that was on these cameras, we drilled a little tiny hole in the enclosure so that if we do get sand inside this time, it will trickle out on its own and we won't have this problem.
Yep, little drain holes. Good lesson from Curiosity. Yeah, it's actually kind of amazing that little sand grains are hopping across the surface and bouncing up 6 feet and going into the front of our, the lenses are set back a little bit. There's like a sunshade and a baffle, so there's a little bit of volume there. And on Curiosity, they're hopping up in there and getting in there. It's totally surprising.
Or getting,
it's like the storms are not, the storms, you know, the winds can be high speed, but the atmosphere is so thin that the power in them is not very high. It's not like it's going to jiggle the rover or tip it over or anything like that, but it can still move sand and obviously dust, but it's kind of surprising how much it can move sand, even though it's such a thin atmosphere.
Yeah, it's like that carved rock, you know, how long it took to do that. You know, that a lot of people have seen the movie The Martian, and there's that scene in the beginning with this violent storm. You know, I mean, it's a dramatic and fun scene, but it's science fiction. I mean, it's nothing like that. I mean, the wind speeds can be very high, but it would be like somebody blowing up, you know, feathers by you. It would feel just so light. It's so thin, but it moves sand and dust very efficiently.
And you're constantly looking towards the future. And so DBL on Twitch asked, what changes have you made to the rover design to better suit the conditions of Mars, which I think Elsa just answered with adding those holes so that you are able to get that dust off. So we'll move on to Harry on Twitter, who's asking, could you please describe the software you're using to stitch together that panorama? Is it custom software developed in-house or using commercial software like Lightroom or Photoshop? If custom, what operating system is used?
Go ahead, Elsa.
Great question. Yeah. Do you want to start, Jim, or you want me to take it?
You start and I'll finish.
Okay, sounds great. So could we have that picture again with the frames on it? It was a second, I think it was number 5. Yes, perfect. Yeah. That is such a great depiction of what my life, what our team's life looks like on a daily basis. This is Homegrown Software. As I mentioned before, John Proton wrote it. He was actually way back on MER, going back now almost 20 years. He was one of the operators that would do commanding and then realized at one point, you know what? I can do this software much better than anything that's commercially available, anything that people have thought of, because he did the job. And then he took his software programming skills, put the two together, and came up with this tool. And it truly is the only software of its kind on this planet. So it's specifically customized for visualizing, imaging, and this is just one way of looking at it, but there's a lot of details that goes into it that's at our fingertips. The distances to each part of the image, what the focus would be that would correspond to it. There's just a tremendous amount of power behind it. So we're extremely grateful to have this. And in fact, it's thanks to Jim working on PanCam with John. And then we did a beta version for Mastcam on MSL that we've been running now for years. All of it with the thought that we would get this tool for this mission with these cameras. And it is spectacularly paid off. It is exactly, I mean, it's more than I could even imagine. You know, Chris and I were talking the other day, one of my ops engineers, And he was just laughing. He's like, I cannot believe this piece of software. I don't even know everything to do with it yet. I can't wait till we can explore it more. And we all feel like that. It's amazing.
So there's a lot of custom homegrown software, but we also do occasionally use Photoshop or those kinds of commercial tools to finish some of the processing and stitching. So it's a mix.
And like you, oh, sorry, go ahead. Go ahead.
Yeah, I just wanted to finish up on the question, the operating systems. We really use all kinds. We're using, some of my team runs on Macs. We also have some Dells. We use Linux. And just throughout, we are a team of hundreds of scientists and engineers. If you count them all up, there's probably thousands. And we use all kinds of tools. Make them all work together. Our tools that we run for the mission that all of us run have to run on all those, well-known platforms.
Yep, and there's all kinds of programming in C, Python, MATLAB, IDL. I got some old Fortran stuff that I can still use. It's a real wide array of programming.
Not only a wide array of programming, but it's a village. And thank you so much for everyone's questions out there on social media. So many of you joined us today, and we'll try to answer some of your questions as we progress through the rest of the day and tomorrow. But thank you most of all to Jim, Elsa, and Kjartan for joining me this afternoon.
It's been a lot of fun, and we just have to thank all of our teammates on the Mastcam-Z team, on the entire Rover team, the NASA JPL team, the folks who built the rocket, the folks who got through COVID to get us to the launch pad. I mean, what an incredible team! Thousands of people involved in ultimately getting to this kind of spectacular imaging.
Yeah. Thanks for having us.
Thanks so much, you guys.
Exciting.
Yes, thanks for having us.
Oh, thank you so much. We can't wait to see the rest of the panoramas. Now, for the latest on the mission, follow at NASA Persevere on both Twitter and Facebook. And you can also take a deeper dive at the mission's website, mars.nasa.gov/perseverance. And as Jim mentioned, there's lots of information about the Mastcam-Z instrument on the website, mastcam-z.asu.edu. And the very latest images can be found at mars.nasa.gov/mars2020/multimedia/raw-images. A lot of great feast for the eyes, as Jim likes to put it. Now, thanks so much for watching this afternoon, and go Perseverance.